Okay, so welcome everyone. As you know, we recently restarted the series this semester, and our focus topic is galactic cosmic rays, measurements and theory. And you should, please take a look at our website. We have an excellent lineup of speakers. And today we are very pleased to have Dr. Andrew Taylor. He's going to talk to us. He's going to give us basically part two of an introductory talk on cosmic rays. So I think the topic is interesting. It's galactic, extragalactic cosmic rays. So maybe you'll tell us more about it. So Andrew has previously spoken in our series. He's been, a regular participant. He's an expert in several areas: gamma ray astrophysics, emission processes, high energy cosmic rays, neutrino astrophysics. He's currently at DESY, Zeuthen in Germany, and he recently has been focusing on cosmic ray propagation, transport, and energy losses, and probing cosmic ray source distribution, AGN acceleration, and emission. And Andrew received his PhD in astrophysics from the University of Oxford. He's a member of the HES collaboration. He was a postdoctoral researcher at FPIK Heidelberg. He was also at ISDC University of Geneva, and he was the Schrödinger Fellow at DES in Dublin before joining DESY. So let's welcome Andrew, and thanks again for giving us this talk. We are recording the seminars, and we will post them on our YouTube archives. So please go ahead, Andrew.
Okay, cool. So it's a pleasure to see you all again. Actually, it's nice. So when this title was proposed to me, Galactic to Extragalactic Cosmic Ray sort of transition. So it came to my mind a talk that I had been to about 10 years ago or so by Tom Geiser, who called upon an analogy between the heliosphere and galactic halo. Okay, so the point was that we reside within the heliosphere, um, which is a bubble that the sun inflates as it sends out this supersonic wind, and that to some extent does some shielding of galactic cosmic rays locally. Okay, and then likewise we reside within the galactic halo, and and particles, of course, could be produced in the galaxy or can be extragalactic. And he was suggesting, I've got to be careful with this analogy. There's lots of differences between these two systems. It's not being suggested that the galaxy sends out a supersonic wind or anything like that. It's not that sort of analogy. It's more of an analogy of being aware that you're sort of near a weakish sort of source class, and that other source classes reside at larger distances, and paying attention to what we can learn from the heliosphere to help us be guided on understanding the galactic cosmic ray spectrum. Okay, so here's a plot or a slide essentially I stole from Tom's talk. Okay, on the left you've got cosmic rays within the heliosphere. Okay, and this is pretty low energy stuff at the MeV scale per nucleon. In particular, I hope you can focus your attention on this part here. This is a sort of a power law distribution that we see of cosmic rays within the heliosphere, which are predominantly particles, solar energetic particles. So particles have been accelerated by solar events, and that's collectively giving rise to a power law spectrum of cosmic rays locally. Those events themselves, we've measured the spectrum from. They're impulsive events occurring on different sorts of timescales. Each impulsive event seems to produce a power law spectrum of its own, okay, with its own Emax, and they sum together to give overall a power law spectrum. And Tom noted with a knee of its own, so that's a softening in the cosmic ray spectrum, and then the onset of a galactic cosmic ray component at high energies. And on the right, you can see here, this is the cosmic ray spectrum that we observe at higher energies. Okay, here we've got a few features. A knee feature, it's a softening of the spectrum going from an index like this to steeper, and some other features, and then eventually a hardening feature, which might relate to the onset of extragalactic sources. Okay, so let's continue with zooming in on the cosmic ray spectrum. So here we've got the knee. So this is at 3 times 10 to the 15 eV or so. This is the total cosmic ray spectrum. Second softening feature happening at about 10 to the 17 eV called the second knee. And then this hardening feature at about 3 times 10 to the 18 eV, which are referred to as the ankle. And we'd like to know the origins of these features and what they can be telling us about the different source classes that are giving rise to this spectrum. Now, a bit of history. In the 70s, there was a discussion, an interesting discussion between Burbage and Ginzburg and others. And the discussion was, or the debate rather, was could these cosmic rays that we observe, even down to the GeV scale, all be extragalactic? Which is an interesting question to consider. And you can ask what would be the upshots of such a scenario. Well, one would be that the universe would be filled in the regions where uncollapsed regions, ungravitationally collapsed, would be filled with cosmic ray protons. And of course, there is target gas out there of low density, but nevertheless, it's present. It's about 3 times 10 to the -7 per centimeter cubed. And therefore, the universe at large has a gamma ray emissivity, would have a gamma ray emissivity. And then you can sum up that gamma ray emissivity and see how much emission that you would be expecting for such a case. And what you find is that you expect a gamma ray brightness of about 2 times 10 to the -3 MeV per centimeter squared per second per steradian for that model. More recently, we've got quite good now at probing the isotropic gamma ray background. So this is gamma rays away from the galactic plane. This is the gamma ray emission, removing resolved sources for this plot here. And if we focus on the GeV scale, we see a flux at the level of about 6 times 10 to the -4 MeV per centimeter squared per second per steradian. So that's below that predicted if the universe was full of GeV cosmic rays, and therefore it places a limit on such a scenario. And I think that's a nice intro into what I'm talking about generally, because it shows how gamma ray observations sort of can shed further insight into what's going on, which the cosmic ray community certainly needs. Okay, so this moves us forward to the present paradigm, which is that cosmic rays or galactic cosmic rays are coming from supernova remnants. And those features that I referred to on the spectrum before, the knee, would really be coming about from the proton knee. So we've got sources accelerating protons up to 3 times 10 to the 15 eV, and they might be supernova remnants that are doing this. And therefore, if the maximum energy is just scaling with rigidity, so you'd expect, sorry, with charge, sorry, as you'd expect, the corresponding knee for iron would be at 10 to the 17 eV. Okay, and then you'd expect in this scenario that extragalactic cosmic rays are kicking in and they are dominating at the ankle, and this leads to this sort of yellow line here. But the yellow line isn't quite the sum of all of these. There's a slight deficit going on, and the deficit that's going on is because we've got the end of the supernova remnants spectrum, and extragalactic sources haven't fully taken over. So we have a question mark on this energy gap between 10 to the 17 eV and 3 times 10 to the 18 eV as to what is the dominant source in this energy region. Right, so this was, to my mind, this was sort of first emphasized by Hillas back in 2005. He resolved the issue. In fact, he proposed a solution to this problem by suggesting that all of the, let's say the protons, for example, there's the proton knee, and that there's a subset of supernova remnants, or class B source in general, population B source, which is not as bright as the full population, but can punch to higher energies and therefore save the day in bridging this gap between 10 to the 17 eV and a few times 10 to the 18 eV. So one caveat you might note with this sort of solution is it particularly predicts a lot of heavyish species in this energy region, which is something that we'll come back to in a while. But Michael was definitely aware of this issue because in 2014, when he gave a talk to some of us on this topic, well, firstly, he had updated his plot with more recent data. One set of recent data he sort of alerted to was that there was some evidence of light component, subdominant components of cosmic rays with a relatively hard spectra in this energy region between 10 to the 17 eV and a few times 10 to the 18 eV. And that should be of interest, and it might be shedding light onto this population B scenario. Okay, so this was this sort of picture, this simple picture, was picked up on also by Tom Geiser. So, well, firstly, just to note, Tom changed his notation. So population A becomes population 1 and population B becomes population 2. So population 1 and population 2 are galactic. And so this is basically a reformulation of Michael's scenario. And this is just Tom sort of showing that this indeed can account for in terms of the energy flux, this scenario can describe the spectrum pretty well. And just another thing to note is that in Tom's notation, this is the spectral index of the sources. It might look a little bit peculiar. That's because his indices are defined in terms of DND log E. So 1.4 here in other people's notation would be called 2.4 if it was just DNDE. Okay, so but the numbers seem quite reasonable, and he's got this is Michael's scenario really, that we've got sources getting up to the knee, a few times 10 to the 15 eV, and then another population which is punching a factor of 10 higher energy than that. And collectively, this can describe the full cosmic ray spectrum. Okay, so that's the Hillas type 3 scenario described by redescribed by Hillas. Okay, but sorry, redescribed by Tom Geiser, and actually Tom took it further than this. So I want to talk about what he said next because it's quite interesting. So it said that that's one possibility, and put that to one side. But we could also be thinking that population 1 doesn't make it to the knee. Okay, so population 1 can make it to about 10 to the 14 eV or so for protons. Population 2 can get to the knee. Okay, and then population 3 actually doesn't even get to the ankle. It gets to below the ankle for protons. Okay, and then this scenario is interesting. It might be able to account for some sorts of micro features that we see in the spectrum. Softening feature that we might be seeing is about 10 to the 14 eV might be from the ending of this population 1 class. And in fact, the picture has improved since Tom produced this plot, because we've now got these lasso results, which indeed show that, well, part of this picture is not even correct anymore, that population 2, we think that now protons at the knee dominate over helium, so that this population, it should be pushed up a little bit. Okay, but the picture by and large still holds that this scenario is sort of an alternative to Michael's population B scenario. Okay, and how do we discriminate between these two different sorts of caricatures? That's really what they are, but they're useful caricatures. So, well, one, and it's highlighted by Tom, is that looking at the mean composition of the cosmic rays as a function of energy. So this is the log A on this on the y-axis. It's a function of energy being plotted. The data seems to show 2 cycles from going light to heavy, and then back to light, and then back to heavy. as a function of energy. And well, that's interesting in its own right, and it needs to be described by this three population scenario, either Michael's or Tom's scenarios. And you can see instantly that there's a problem with what Michael was suggesting originally. I mean, it's what we noted sort of earlier anyway. So look at this brown line here, that Michael's scenario stays heavy in this transition region between 10 to the 17 eV and a few times 10 to the 18 eV for this scenario. That's to do with where you place these three populations in the maximum energies. And to solve this, in fact, that's exactly why Tom lightened or reduced the maximum energy of population 1 and population 2, was to sort of resolve this tension with the log A evolution. But we always had this caveat that the data is quite limited at the moment. I mean, this is you'll see on some later slides some other log A data, and it's quite messy, and it highlights the need to improve measurements of log A as a function of energy in this energy region between the knee and the ankle, because particularly the composition is able to help distinguish these different scenarios. But the point is, we're just playing this game where we're moving population 1, 2, and 3. The population 2 is kicking in and starting to dominate over population 1, just as the composition would start to get heavy because of the decrease of the protons from population 1. Okay, then at 10 energies about 10 to 17 eV, where the composition has become heavy because we're at the heaviest nuclei, or the largest charged nuclei for population 2 is dominating the spectrum. That falls off very quickly, and we have the onset of population 3, the proton component of it, which would make the composition very light very quickly, and that leads to this very fast transition in log A in that region there. Okay, so that's that's the situation in distinguishing between these two scenarios, and the need for having better log A measurements for distinguishing these scenarios. Okay, what physical realizations of these scenarios might be taking place? Well, for particularly Hillas's type of population B scenario, extreme supernovae are often been called for in the literature. So I'll put some references here for people to follow. The point here being that most supernovae might be only able to get to the knee energy, but some special subset with very large explosions energies and small ejector masses, and that was emphasized in Christopher Fari's paper, could hope to push even beyond 10 to 15 eV and lead to this scenario where even at 10 to 16 eV we're getting protons up to without a cutoff. Whereas, and this is sort of, I know Brian's not able to be here today, but him and his collaborator here worked on this scenario, supernova in different environments, in massive star cluster environments, and where they go off can change the maximum energies that can be achieved. And that's what's been realized here, where we've got most supernova not even making it up to the knee energy. So this is more like a geyser type scenario. And whereas some special supernovae that go off in massive star clusters and on the edge of the clusters can push up to beyond or up to the knee and a bit beyond. And here's the log A data for this scenario, which is similar to what I showed earlier for Tom's log A evolution plots. But this plot actually shows how ugly the situation is, a bit perhaps uglier than that Tom showed, because including here results from some other data sets like Tail and Tunker, etc., showing how confusing the situation presently is in terms of inference of log A. Okay, so we can go further though. Once we've got these different populations, we can ask ourselves, well, what power of sources need to maintain these different populations? For population one, we get the same argument. I think Stefano went through this 2 weeks ago, that they need to have a sort of a collective luminosity of about 10 to the 41 ergs per second to maintain, particularly at GeV energies, the density of cosmic rays that we observe. But if we're having a source class which is only taking in at about taking over at about 10 to the 15 eV, so 6 orders of magnitude above the GeV scale, then because of the difference in time it takes to get to steady state for GeV particles compared to, sorry, for PV particles compared to GeV particles, that leads to a few orders of magnitude reduction in the luminosity needed for population 2. So that comes down to a few times 10 to the 39 ergs per second, which is quite a bit reduced compared to that needed for supernova remnants, and it actually opens up the realm of possibility more broadly, because there are quite a few source classes which can satisfy this requirement. Okay, and it's interesting to note also that if we balance the acceleration rate of particles in our accelerator, so this is the Lamb radius of the particle, this beta here relates to the velocity of the shock for shock acceleration, and this eta is saying how close to bone the accelerator is taking place at, which we'll set to unity for these calculations. And when we balance that with our escape time, we get Michael's maximum energy Hillas criterion here. And then if we likewise we think of the magnetic luminosity of our source, which relates to the magnetic energy density and at a radius being thrown out with a particular velocity, and we can balance this or relate the magnetic luminosity of our source to the kinetic energy of the luminosity of the source with this factor eta b, then we can recast our maximum energy requirement in terms of the kinetic energy luminosity of the source, the velocity of the material as it's throwing out, which relates to the velocity of the shock. So here it's being set to 0.1, and eta b, so the magnetic fraction in terms of the luminosities, also being set to 0.1. And what we find is for sources which are able to have kinetic energies of the order of 10 to the 38 ergs per second, that we can get to the PV scale is achievable. Okay, so that's interesting, because considering source classes which can be working as this population B, that we can start to think about which sources can get to the PV scale because if they have enough kinetic energy luminosity, and there will be enough of them to maintain the present population. So what's interesting, so if we think about microquasars, they are binaries or a black hole with a companion star that's feeding the black hole. It's if it's accreting, and there's good reasons to think that they are accreting close to the Eddington rate, then we can, calling upon 10 to 38 ergs per second is quite reasonable. So it motivates that microquasars should be considered as potential PV candidates. And in fact, it was shown by Gwinnell and his collaborator here that scenario can account for the cosmic ray spectrum as basically going over the Geyser population B scenario that we went through earlier. So that's very nice. But even more exciting, I think, is that now there's gamma ray observations which are sort of further supporting this scenario. There might be shedding light on in a way that just cosmic ray observations on their own can't quite achieve. So here we've got some of the gamma ray spectra seen from the microquasars. Well, a few things to note. Their spectral index is sort of similar to that's pushed in Geyser's population B scenario, of the order of 2.4, and sometimes actually a little bit harder than that. And also that in terms of their maximum energies, these are, of course, this is the gamma ray spectra. But we're seeing with these gamma ray spectra that they're staying hard and their cutoffs seem to be occurring at above the 100 TeV scale, which would mean that they're if this is hadronic emission, and there's good reasons to think that this is hadronic emission, that they are indeed PV accelerators. So a coherent picture starts to emerge, and it nicely attaches to Guy's population B scenario. That's not the only possibility in town, though. Star cluster winds have also been proposed. They can also get to close to Eddington luminosities. A lot of these similar arguments, they don't quite have winds at the 0.1c level, or shocks at the 0.1c, but still they motivated as a possible alternative candidate for this population B. Okay, so I think that's progress with in terms of what we can say about population B, where its maximum energy needs to be, and what sources might be responsible for it. What about population C? Can we say anything about population C? Okay, so earlier on, at the beginning of the talk, I mentioned that Michael Hillas's talk in 2014, he was noting that there was some sort of subdominant light components of cosmic rays that might be present around the second Ni energy range, so about 10 to the 17 eV. And that's what's shown in this plot here on the top left. So here we've got the full cosmic ray spectrum, and we've got decomposition of the full spectrum into a heavy component here, which softens just below 10 to 17 eV. And then there's this subdominant light component, which seems to have a hardening feature also around 10 to 17 eV. And then this more recently has been sort of gone through with updated hadronic model interaction models, and largely the same picture is being uncovered. That if we look at these blue points, which is the light component, we see a hardening of this light component. It's not that this light component is dominating the cosmic ray flux; it would only start to dominate close to the ankle energy range or so, but still, it's a hardening feature, and if we see a hardening feature, there's good reasons to think that hardening feature is happening because of the onset of a new component, which is again quite like Tom Geiser's population B scenario. Okay, so can we constrain this population B component? So in an analogous way to what Ginsburg and Burbidge were thinking of in terms of a constraint on what if GeV cosmic rays could be extragalactic, which I covered earlier, you can place a similar constraint on cosmic rays at 10 to 17 eV, because of course the universe is also filled with ambient photons, CMB, for example, and so cosmic rays with energies of around 10 to 17.7 eV will interact with these background photons and can lead to pair creation. Okay, so we did some calculations on this a while ago, and we propagated cosmic rays from these extragalactic sources and let them interact with this background radiation. And this leads to a softening of the spectrum. So the dotted line, which shows what the spectrum is like if the cosmic rays just didn't interact. Okay, and the solid line takes into account this interaction, this absorption of the cosmic ray energy flux, and converts it into an electromagnetic cascade. Okay, so this is for one scenario in terms of how that source class of extragalactic sources evolves with redshift. Okay, so this is that the source class evolves like the star formation rate, okay, with redshift, up to a redshift of around 2 to 3, where the star formation rate peaks. And on the right here, we've got a similar set of calculations, but assuming that the source class, this extragalactic source class, does not evolve with redshift. So in that case, there's much less absorption of the energy flux, and that makes very good sense because essentially our sources on average are more local than the scenario on the left. Okay, and then we can look at how much energy is feeding or being reprocessed from this. But what is that reprocessing? Let's quickly cover that. So those pairs produced through that beta Heitler process go on to do inverse Compton scattering and the energy photons produced more pair production in a repetitive cycle that leads to an electromagnetic cascade. At high energies, these two processes are very similar to each other. In some ways, there's a symmetry to the whole system, and inverse Compton and pair creation are indistinguishable. The cross sections are very similar, and the energy transfer between particles is very similar. So, but this symmetry it stops at around 10 to 15 eV, and the reason for that is deep down there is a difference between pair creation and inverse Compton. The big difference is the cross section for pair creation has a threshold, whereas inverse Compton it doesn't, and that leads to suddenly the pair creation length increasing as we drop in energy, whereas inverse Compton only has a very mild increase, and that means all of those pairs will pump back energy into photons. So eventually, all of the energy trickles back into photons. And at what energy range does this happen at? Well, between about 100 or a few hundred GeV and a GeV. Okay, is the place to look for that recycled energy through pair creation. Okay, so that shows us, well, that explains these plots here that I'm showing for the reprocessed GeV photons produced for this scenario on the left, where the extragalactic sources evolve like the star formation rate, and on the right where they don't. Let's just quickly look at this isotropic gamma ray background data, which I'm showing here, which is similar to what I was showing earlier in my talk from the Ginsburg and Burbidge discussion. At GeV energies, it was 6 times 10 to the minus 4, but that was in MeV. So this is 6 times 10 to the minus 7 in GeV, per centimeter squared per second per steradian. For this plot, we decided to focus more on closer to the 100 GeV range. And not only we care about the isotropic gamma ray background data here, but by this point in 2016, the removal of unresolved blazars had been removed on top of this data. So the limits had come down essentially. And that was interesting because that meant that we could constrain that this extragalactic population shouldn't be evolving like star formation rate. Otherwise, you hit a bit of a crisis, and over producing this isotropic gamma ray background. And this was always a concern because there's other contaminants of this isotropic gamma ray background which still haven't been removed. So hitting this limit is a big issue. And that means that this extragalactic population, which we think really is existing at 10 to the 17 laser energies of 10 to the 17.7 eV, it shouldn't be evolving quickly with redshift at all. And it makes essentially what it's saying is that the sources should be, even if they're extra, should sort of be local and extragalactic. Other arguments were also considered in the community. Marcus Arles looked into what neutrinos might be produced if these similar energy cosmic rays were extragalactic, and again, this is talking about how the sources evolve with redshift, and even just using Amanda data back in 2005 could constrain this scenario. However, it should be pointed out this came with a caveat that these calculations only assumed that the cosmic rays were protons in this energy range, which was something that was being considered back at that time. And it's something that we've had to move away. Well, we've moved away from because the observation data in terms of essentially the log A data at higher energies suggests that the composition does get heavier. So it pushes against, moves away from this scenario. In fact, Marcus went on to sort of bring these things together and highlight that the the Ice Cube data in 2009 was compatible with the with this scenario, given that only a small fraction of cosmic rays were protons at high energies, and what their actual Emax indeed was compared to what had been considered back then. Okay, so I want to move on to now to talk about this environment that Tom brought up in his analogy. So the galactic halo, and how understanding it might be useful for the understanding this population B and C components. Okay, so if we look at the diffuse gamma ray emission, we see that we see emission from above and below the galactic plane, which we think is coming about from also non-thermal particles in the halo region. Okay. Furthermore, this is GV gamma ray emission being shown in this plot here, and on top of that, there seems to be evidence that there's hot gas that surrounds this emission. And these are at distant scales. For example, these bubbles go up to 8 kiloparsecs or so, that we're certainly in the halo environment that we should be thinking about, and we're interested in probing. Okay, well, the good news is that we've started to understand this halo environment much better over the last 15 years. So that started back even in 2012, absorption features along lines of sight, looking at AGN along different lines of sight, showed the presence of an absorber, and there was an absorption feature seen towards different AGN that was suggesting back then that there was a large amount of hot gas, ionized gas, that could be doing this absorption. Okay, that moved forward, I think, a bit further by ram pressure stripping calculations that were done looking at satellite galaxies and how much ram pressure stripping that they should be exposed to as they move at, say, 100 kiloparsec distances around the Milky Way. And they were inferring densities of the order of 10 to the minus 4 per centimeter cubed back then. But I think we took our biggest leap forward was with E-Rosita data and looking at the X-ray emission of Milky Way mass galaxies and looking at this hot gas emission in X-rays as a function of distance from the galaxies. This was fit with this sort of King function here, and it was inferred that this hot gas seemed to be dropping off like 1 over R around the galaxies. But so this picture's moved forward, and it all seems quite consistent. There's the dominant fraction of baryons in the Milky Way in terms of components seems to be in this hot gas phase, and we also seem to understand how this gas drops off with distance in terms of its density. Okay, we can even though those fits before were with assuming this King function profile for the gas, we can ask ourselves a question: what would the gas profile look like if the gas was in hydrostatic equilibrium? Okay, for an isothermal gas, the gas seems to be roughly isothermal over the distances that we're talking about anyway. And so to know that shape of the gas for this scenario, all you need to know is what the shape of the galactic potential is. The galactic potential is roughly is called the log R potential sometimes in the community. That sort of indicates the potential just doesn't drop off very quickly at all with distance, hence why we get flat rotation curves. And that leads to, because the potential is a log R potential, that means you get a power law distribution expected if the gas is in hydrostatic equilibrium, and that's what's seen shown here. So even though the King function was adopted previously, that doesn't mean that the distribution is really a King function, and in fact, it's been motivated by the community that the gas looks much more like it's in hydrostatic equilibrium, and it's certainly consistent with it. So we understand quite well now, I think, the nature of this hot thermal gas out in the halo. And you can move forward if you do simulations. You start the gas in these simulations. You start the gas off in this hydrostatic equilibrium, but you make the halo hot through a heating process. You can drive a slow outflow from the Milky Way, and that outflow of gas can advect cosmic rays, and those cosmic rays can interact with that target gas. The target gas really stays similar to the hydrostatic, because we're talking about subsonic outflow. That target gas would stay largely in the hydrostatic equilibrium distribution, and it can give rise to a Fermi bubble-like structure in this case. So that's interesting because it brings a consistency, if you like, to, or a simple description that can explain how we might get some of this emission that we're seeing above and below the galactic plane. However, let's take an aside and think, what is it that let's say ignore this advective process? It's just think of the diffusive problem of cosmic rays from the disk into the halo. When people typically do this, they put an absorption boundary for the cosmic rays getting out into the halo. Or in fact, they talk about pretty small halos of the order of, let's say, 4 or 5 kiloparsecs seems to be a preference. Okay, if you do that, you have sources sources in the disk, and the problem is essentially quite close to a 1D type problem. The sources are pumping out particles, and then once the particles diffused and get absorbed at the edge, you sit into steady state. Okay. And then this has been used to infer things like the boron to carbon and beryllium 10:9 ratio and things in the community. But it's been noted that there's a danger in doing this. This has been noted by Hopkins, for example. And I mean, the halo size being inferred in these pictures on the left here is not really representative of any scale lengths of magnetic field and free electrons, but rather it's just talking about the scales over which the cosmic rays have an order unity probability to return to the disk and interact and make secondaries. Okay, but as we know, even if you just pumped cosmic rays into or pumped them and you let them diffuse locally, it will look like, but eventually it'll get to steady state, and it'll get to steady state because if you're doing 3D diffusion, has been known for quite a while, you in 3D diffusion, you have a good chance to not return, in fact, as you propagate. And this was nicely put by Shuzio Kakutani, that a drunk man will eventually find his way home, right? But a drunk bird may get lost forever. Okay. The point is, and it's the same point that Hopkins is making here, actually, that even if you don't have an absorptive boundary, you'll get to steady state through just diffusion alone. And those particles that get out there, they don't tend to return just because of the growth in phase space. So it's an interesting point to note. And it's a sort of a criticism of the community in that you can get descriptions sort of that work, but it doesn't mean that you're addressing reality through these scenarios. particularly because we know that giant halo does exist. Okay, so that's just showing you here what the plot of the distribution of particles looks like. And there's the difference here is for the small halo community, this is what the distribution of particles looks like. For the large halo community, you get this very long tail of particles out in the halo. And they might have an emission signature to go with them. And this has been noted by Kalashev and Troitsky and others. So here I'm showing a few curves here, but if you focus yourself on the cosmic ray density as a function of distance for the diffusion scenario, which is just what I showed you on the previous slide, and what they did in this paper in 23 was they convolved this cosmic ray flux with this target gas, which we now know exists out in the halo. And they asked us, well, how much neutrinos might be produced in this scenario? And they got that the neutrinos from the halo was comparable with that in the disk for such a case, which is interesting. They also asked some other distributions, what the emission would look like for other distributions. And it's interesting to ask why they did that. The motivation for asking that question came about from looking at the gamma ray emission that was being seen from M31. So it's our nearby galactic extragalactic neighbor in our local extragalactic environment. So here's the Fermi map of M31. You can sort of appreciate that there's some sort of emission that's happening locally to M31 on the, let's say, tens of kiloparsec scales and a few degree scales. But Moskalenko and others were motivating that even on 10 degrees, there seems to be evidence of emission from M31. So that's sort of appreciated here on the right. This is the energy flux as a function of energy from M31. Here is the disk emission, but this is in terms of brightness, okay? And here is this sort of halo emission, let's call it. If you multiply this halo emission by the angular size of the region, you appreciate that this is actually a considerable amount of emission that's coming from the halo in this case. Okay, and it was this observation that motivated Kalashev and Troitsky and others to consider other scenarios and therefore pump up the emission in the halo. Because and the physical reason for that would be, even though this is just considered a diffusive propagation scenario for one of the cases, there's reasons to believe that perhaps advection, like I mentioned earlier, in fact, advection is also at play here, and that might be changing the abundance of cosmic rays in the halo. Okay, so that brings me on to the last topic I want to cover, which is we now know this halo exists, but one of the big things we don't know about the halo is how magnetized it is. Okay, and how might the level of magnetization of the halo affect our perception of our population C sources? So I mentioned that this halo is hot, and I've also mentioned that the densities that we might be thinking of at 100 kiloparsecs might be 10 to the minus 4 per centimeter cubed. So collectively, that tells you that there's a lot of thermal pressure in the halo, right? Well, if it's in hydrostatic equilibrium, you know that it's not the thermal pressure is not dropping off quickly; it's dropping off like a power law, like I showed earlier. Okay, therefore you can infer what the magnetic field might be out in the halo if the plasma beta for this gas is of order unity. You'd be expecting B fields of the order of 0.2 microgauss or so out in the halo. And that would have consequences because the Lam radius of cosmic rays, even at 10 eV, is of the order of 50 kiloparsecs. So if there is this sort of 0.2 microgauss magnetic fields out in the halo, then they would be significantly deflected in that region. And one of the reasons you might be interested in considering such field strengths is because Heeson, using stacked measurements of looking at what's called the residual Faraday rotation along lines of sight which clip nearby galaxies. So because they're nearby, they're nice and extended in the sky. And he's been trying to probe the magnetic fields out in these regions, and he's got numbers, or he finds numbers which are somewhat similar to this inference by Fairman. So it's certainly warranted considering such magnetic fields. Okay. In terms of the cosmic rays and the sky maps that we see, below 10 eV, we see sky maps which are dipole-like. And above 10 eV, we start to see multipole structure, or apparently multipole structure in the sky maps. And an interesting question is, can this observation be squared with a magnetized halo? Okay, so let's do a little experiment then. So here we have a source of cosmic rays, extragalactic cosmic rays. They are moving off. These arrows here are meant to be telling you what the current is of cosmic rays as they move away. And then we put around us, we put a region with a reduced diffusion coefficient. And the currents are sort of being shielded from this region because of this reduced diffusion coefficient. It's just such a scenario. And this would have real consequences in terms of what we would observe, certainly as a function of energy in such a case. So let's look at that next. So if we inject cosmic rays from our local extragalactic source and we propagate them through this, well, let's first off on the top here, we just ignore, we turn off any effects from the magnetized halo. We can inject a dipole, of course, or a point source. Or in this case, it's actually 3-point sources. And if we then propagate the cosmic rays through our magnetized halo, we can either, for the dipole case, we just see a dipole, but its dipole strength is reduced. Or for the beam case, we see a dipole, and for the 3-beam case, we see essentially a dipole as well. Okay, and what's going on in this case is this is the injected map and this is the observed map in terms of the power spectrum of the cosmic rays. And what the magnetized halo is essentially doing is it's reprocessing power at high multipoles and pushing it to low multipoles, such that we're always seeing a dipole even for the 3 cases. Okay, but you can distinguish between these scenarios by looking at how the dipole changes as a function of energy. Okay, so here's the plot of the dipole strength as a function of, well, scattering length, which essentially relates to the dipole length as a dipole strength as a function of energy. So here's the growth in the dipole for these 3 cases, the injected dipole, the 1-beam, and the 3-beam. And here's the growth of the quadrupole moments, also as a function of energy. And the rapid growth of the quadrupole compared to the dipole is one way to distinguish this scenario. This is what it sort of predicts. In fact, essentially using the quadrupole to dipole ratio and as a function of energy is you're able to use the observations as sort of a probe, a Hall probe of the magnetic field in the halo region for this case. So certainly this idea would be testable for the future. Right, so that brings me to my conclusions, right? Firstly, the transition, well, there's good reasons to think that the transition between galactic and extragalactic cosmic rays is happening between 10 to 17 eV and the angle at 3 times 10 to 18 eV or so. The population B class is required to bridge this gap, because as Michael highlighted at the beginning, otherwise we have a bit of a mystery as to how we can make enough flux in this region here. Okay, and there's actually we've got this from gamma ray observations, we've started to have physical motivations for what this population B might be. Our third population, our extragalactic population, is starting to be constrained. It's hard to constrain it, but we certainly can say things like what its source evolution cannot be. And in some ways, it seems sort of local is, we can redefine what local means, but local in some sense is preferred. Okay. We're learning a lot about the halo presently, and we can learn a lot in the future about the halo from looking at secondary signatures of cosmic rays in the halo, in terms of the emission even above distances larger than 10 kiloparsecs. And then lastly, the magnetization of the halo, which is not known at the moment, but it being magnetized, and there's reasons to think it should be magnetized, will have implications on the penetration of our extragalactic cosmic rays into the region, and these can be tested. Okay, thank you.
Thank you very much, Andrew. That was great. We have time for questions. And Felix, do you want to lead this session? I think we have a question first from Dimitri.
Yes, could I ask? Hi, Andrew.
Hey, Damon.
So my question is, when you do this big halo modeling of the nearby stars, do you take into account inner part of the halo deflections of cosmic rays in the galactic magnetic field models?
So the deflections are no. So you're talking about the latter part of my talk, where I was talking about the shielding effects.
Yeah. But when you look for the anisotropy maps, you show the maps which are seen on the Earth, right? So these are affected also by intermediate field inside of the galaxy.
Yeah. No, these don't take into account subsequent deflections very locally. They're only using propagation through an isotropic turbulent field throughout the halo.
Okay, I see. You probably could look. We recently, with Peter Tinnikov and Korechkin, made this look for the difference between OG&TA data and found that these local models could resolve this difference and at the same time predict the position of such source around M82. So you could look if this halo would, but the question with big halo is a question of its magnetization mostly, right?
That's right. Yeah.
So it's interesting to see how it's consistent. Okay, thank you.
I know the paper you mean as well. But I wanted to, my focus here was mostly on the big halo because I thought that was the connection I could make to other topics.
Sure. Thank you.
Okay, next, who is Susumo? Susumo, only one question.
Okay.
Don't worry.
Hi, Andrew. Thanks for the great overview. So also on the same topic that Dima asked, it's I guess it's related. Well, personally, I have some reservations about interpreting the rotation measurements of Heathen that I've chatted with you about this before, but it's a possibility, so it's definitely worth considering. So I was wondering if how much a strong magnetic field in the halo might affect not just the anisotropy, but even the spectrum.
I guess in
principle, in principle, it could be something like a rigidity cutoff. Maybe.
But you're right, but that happens at much lower energies. You can work out at what point this rigidity cutoff, like real shielding, as I call it, what happens at, and it comes down, and it's much below the energy scales at which we've probed this population C, and I don't see it as being possible in the nearish future, seeing this, let's say, sort of real shielding of the flux.
Yeah.
Effect.
Okay. Thanks a lot.
Nicola.
Hi. So I have a question on this last slide. So my understanding, this one of the quadrupole.
This one.
So my understanding, but I may be wrong, is that basically no higher order multiple that you might have at the edge of the halo would survive at Earth when it is observed, because in the diffusive regime, you will expect only the dipole to survive.
Yeah.
So how would you comment?
But that's a function of energy, Nicola, right? So at low energies, that's true. But then as your particle's alarm radius gets a bit bigger than the coherence length, okay, and your scattering length is growing quickly, you lose this effect, and you start to see the higher order multiple.
Okay, so you're basically working on at the edge of the diffusive regime.
Exactly.
Okay.
It's the transition of the two that I'm particularly interested in, because I don't know if I don't have it on these plots. It's in the paper though. I put where on these plots is the particle's alarm radius is bigger than the coherence length, and you can this transition is really happening as you do that transition.
Okay, thanks.
Well, maybe there'll be more questions. Let me just ask myself. Andrew, you put there that in conclusions that transition takes place around 10 to 17.
Yeah.
And 10 to 17, it's very hard even for microquasars because this relation between power, mechanical or point of view.
Yeah.
I think so. You need 1041 arc per second.
Yeah.
So what is the suggestion? I mean, except for galactic center, we don't have other sources, even most powerful microquasars for 10 to 17. And on the other hand, we have quite nearby, like CNA, which could give you 10 to 17.
Yeah, right. So just to check your question, Felix, so 10 to 17 would be the end of the population B component, right? So that would be the iron for microquasars would be getting to 10 to the 17 eV. So I think that's it. It fits. I think that works. But then your question, I think, is which extragalactic sources are taking over at this energy, or energies a bit above, as is done in the geyser scenario. And yeah, my answer to that would be these local extragalactic objects like CNA would be powering even at those energies.
Or galactic center.
Or the galactic center. It depends on what the maximum energy it can be achieved in the galactic center is. Yeah, but that's the only other question is, how do cosmic rays from the galactic center get to us? Because even this scenario that I painted right here, right, with this advection profile that we get from our simulations, hundreds of kilometers per second, for example, are being achieved, and this is advecting particles away from the galactic center into the halo, and that's what could be giving rise to the Fermi bubble emission. But it's very hard to get a flux of cosmic rays, a sizable amount of cosmic rays in this scenario arriving, unless our understanding of the transport of cosmic rays is quite wrong there.
Yeah, and on the other hand, I think
Hello? Sorry, can you say again, Felix? Reshmi, can you hear Felix?
No, actually, Felix, you're cutting off. Could you repeat your question, please? We don't hear you. I think we may have lost Felix.
Okay, Reshmi, continue. Another questions,
Yeah,
maybe when.
Well, meanwhile, if there are any other questions, I think Felix has some audio questions.
Oh, Paolo has got a question.
Hello, Andrew. Thanks for your seminar. I mean, I had well, I have two questions. One is really about the transition. You wrote in your conclusions that you have from 10 to the 17 to the 10 to the 18.5. So 10 to the 18.5 would be the ankle. So it would be less. And so your population B, what Hillas was introducing was something that filled the space from the knee to the ankle.
Yeah, and that population B, I think, is perhaps galactic.
You think this is galactic? Well,
no, I'm more like trying to caricature the situation, really, because I find it useful. So so Hillas had one scenario where you had one population getting to the PV, a subdominant population B, which was getting to about 30 PeV or so, and then the transition was happening much closer to the ankle. Okay, whereas Tom Geiser, in his alternative caricature, reduced those population A and B components, right? So in my conclusions, all I was trying to say is that those are the scenarios that are covered, right? This transition. If you want to know about my opinion is that the Geiser scenario seems preferable for presently with the current data at the moment. It just seems to fit a bit better together in terms of the limited understanding of log A and things. It seems to work, and that would require that the transition is occurring for extragalactics kicking in below the ankle, and this is in the 10 to in energies of a decade that's 10 to 17 eV.
Okay. Well, I mean, I've always been disturbed by the fact that you do expect that the transition to extragalactic should present as a hardening spectral feature, because your one component is overtaking the other one, and in the energy range between the knee and the ankle, you have no clear hardening feature except the one very close to the knee, the so-called low energy ankle. And so maybe I wanted to invite you a comment on this. A very popular explanation is to have the second knee at the transition. But this is, seems to me a very fine-tuned solution. So let me, before letting you answer or comment on this, I have a second question. It was unclear to me. I think it was very appropriate to introduce a discussion on the Fermi E Rosita bubbles, which are a structure of, I think, extremely interesting and very important to understand the galaxy. I mean, but I had the impression that you discussed the halo as a stationary structure. And I thought it was very robustly understood that these bubbles are transients, that there is a clear, the sharpness of the edges reveal the existence of a shock. And so that you have to treat them as a transient and understand its transient nature. And that it is at least 50% probable, if not more, that this is the vestige of a jet-like emission from the galactic center. If you could comment on this.
Okay, so I don't think the evidence is overwhelming that that's what's going on. There's a few reasons for this. We see it's very hard to probe the evolution of the velocity structure of the gas in the Fermi bubbles, but there's been there have been probes of clouds in the bubbles, and looking at those clouds have emission lines, and we can look at that velocity structure, and that seems to show a deceleration of the gas. Of course, there's caveats that the clouds might be not moving quite as this hot gas is moving, etc. But there seems to be a problem there, and even in the existence of the clouds is a bit confusing because those clouds shouldn't be able to reside for very long, etc. So the velocity structure that we can infer from those clouds seems to suggest that these bubbles are moving slowly, and they're not supersonic. That's another weird thing. Again, from these observations, so they don't seem to be supersonic, and they seem to be decelerating with distance. And another reason I'm not convinced that we're talking about any supersonic outflows from the galaxy is the gas density distribution itself. If it's supersonic, then ram pressure is going to be dominating over thermal pressure, and the gas density should be dropping much faster with distance in that case, just like it does in the heliosphere, right? And that doesn't seem to be what we're seeing. We seem to see that this gas in the halo seems to be in hydrostatic equilibrium, or consistent with like it being in hydrostatic equilibrium. The Milky Way doesn't have supersonic outflow associated with it, and given this is given these constraints, that's sort of pushed me to develop or consider this subsonic outflow scenario that I've been pushing forward. But it's built on these sub-arguments as to what the gases look like. I'm not sure, though. You're quite right, though, that if this gas is really in steady state, or if there are episodic cycles that leads to its structure or not, I don't know at the moment. And you're right, there is some. Looking at the chimney at the base of the bubbles, there does seem to be evidence that this is some sort of transient little episodes that release energy. We don't know if that energy is the jet or if it's star formation. So we've got to be careful about committing to one scenario, I guess, there. And going back to your first question, Paolo, about this hardening feature. It's true, you're right, that we normally do look for a hardening feature to say that something has for a new component, and I would have just appealed to this light ankle, as you might call it, as the evidence as it is at the moment, that there's this new component kicks in below the ankle, but it's hard to see. But I do also remember that, like Michael Hillas emphasizing, that you can easily mask this transition of a new component. He went to some trouble in the early 2000s to be adding components with different normalizations together to show that you can lose this easy evidence of a new component just by adding two components together, and it's sort of getting washed out. So I'm wary of looking at the total flux and seeing evidence of a new component that way. But that's all I can appeal to at the moment, to say, yeah, this hardening feature in the light is to me the best that we have at the moment of that this extragalactic component is happening below the ankle.
Andrew, do you hear me now?
Yeah.
Hello. Okay. Sorry, I just want to continue and relate it to these spectral features. As long as we have degeneracy between the composition and rigidity, I think it's a bit risky to build a model like where is the knee, where is the after the knee. And so in that sense, I haven't seen in your plots the recent PV measurements by Lasso. And that is a cut case when you really, then there's no uncertainty related to the composition. And that is clear that we have several PV, PV particles. So I think it's better I mean, before to go all this modeling, we need to be sure that we're dealing with protons, or we know which nuclei are responsible.
Yeah, so you're right. The closest I got to that was this comment here on slide 10 that Tom's plot here needs to be revised because of this paper that came out November last year on the archive, which tells us that the proton knee seems to be, or protons dominate at the knee, and therefore, yeah, this model needs to be revised because it doesn't account for that, like this update in the data. So,
but for this topic we are talking today, we need them beyond the knee, and in that sense, only isotope has a good data. I think we have relatively good data, and I haven't seen in your plots also isotope data. I mean, about 10 to 17, because cascade is quite very uncertain. I mean, if you look at papers, I mean, so it's really good to deal with proton. And so to some extent, proton data around 10 to 17, even 100, it comes basically good data only from isotope. So that was, I was wondering why you didn't discuss this part. I mean, experimental part between 10 to 16 to 18 or 10 to 17. Quality of data, and how we are sure that we trust this data as proton data. You just mentioned this could be heavy ions, that it changes the situation significantly, right?
Yeah, I mean, isotope is referred to. It was not the data was. You're right though. It's in when Tom gave his or produced his slides back, 2013. He could appeal to the data as it was back then. But yeah, what you say is true, that updates of that data and these sorts of corresponding plots need to be made. In fact, giving this talk has been motivating me to sort of start to revise these plots and to do an update on the details of the spectra that we've made over the last few years since Tom's plots were made. So I can just say I wanted to cover a bit of ground, so I didn't commit to making new plots for the talk as opposed to sort of focusing on just on this first part. But you're right that new data does exist that it somewhat improves.
Why I'm asking Andrew this question, not just simply to use new data, because 10 to 17 is really very critical. I mean, critical for galactic part. So these seminars we will have until the June May are just for where it's more in galactic part, right? So in this in this your presentation, what we'd like to get, what could be contribution of galactic sources, could they in fact provide 10 to 17 EV particles? And in case we come to this degeneracy between composition, rigidity, that was just my question, because there are two problems, as I mentioned. One, to get 100 PV protons, let's say, then it's really difficult because we need a power. So microquasars, even super Eddington, hardly could provide 10 to 41 per second. Then remains galactic center, which in principle could provide. So I already said that. And the second problem is that these highest energies, 100 PV, especially the particles, we cannot be very far from us, if galactic, because they will escape before reaching us. So there are two basic problems, and which I had formulate. Do you really have contribution of galactic sources to the 100 PV? So that was just, I understand this still is not clear. But what I want to say, this HILAS And Geyser, all my respect to, of course, this great stuff they did, but nevertheless, it needs some rethinking, and we don't have much more data, but still we have isotope. But also there are problems with acceleration. And acceleration is easier problem, not the power in general, but because we don't need much power for cosmic rays, but power, principal power in mechanical or poetic flux or whatever. And that's a great problem. And second problem is propagation. Such energetic particle will escape before coming to us unless they are very nearby, located. This is just comment. It's just it's not a question.
Yeah, but I said it before. Just to repeat again. What's appealing with Tom's description is that the galactic cosmic rays go up to 10 to the 17 eV only because that's where the ions accelerated up to, which reduces the constraints, let's say, on the maximum energy of the galactic sources, and that pushes the requirements onto the extragalactic sources to be sort of starting to take over in this region. So, and that seems to be consistent with the log A data. That seems to be reasonably consistent in terms of this rapid. On this slide here that I'm showing, this quick change in log A, at least from the data back then in 2013, seemed to be consistent with Tom's 3-component description. But I also see your point about sort of zooming in on this 10 to the 17 eV and seeing what the updated data says now.
Yeah, and that is just my comment, because 10 PV, it's relatively okay. I think also we have these pivotrons, and not, you can say, okay, only factor of 10 is more, but this is principally, if you take maximum energy, then it's square the powers. You need 100 times more powerful sources. That was so it's very, very interesting. Then when we say only galactic center, but then galactic center, there's a second problem, could reach us the 100 PV particles from galactic center before, in the way they'll escape before coming to us. So that was a very interesting question, which still, as I said, 100 PV, it looks like is okay now. It's galactic, and there are sources, and that not the principal problems. Maybe still is the propagation problem, but for 100 PV, that is something which still will be considered, because this Geyser Hillas plots are a bit not superficial, but formal a bit, right? So just try to get it. And we only recently discovered or rediscovered that to get highest energy particles beyond 10 PV, we need a huge power. And we are happy that we have microquasars, but as I said, for 100 PV, even microquasars are not sufficient. So
it does fit together if microquasars accelerate iron up to 100 PV. So that, and then you're not you're not asking too much of microquasars in terms of their maximum rigidity, but
the problem is we don't have a composition. That is a big problem now, and we are lucky that now we have this lasso data for 10 PV.
At the moment, right?
Beyond that, we don't know. Yes. Anyway, other questions? Okay, looks like no more questions.
We don't have any more questions. This was a very nice discussion. It was a very nice introduction, Andrew.